Hello everyone and welcome to the beginner tutorial on building your very first neural network. This tutorial will teach the essentials of how neural networks work and their fundamental basis. You'll be programming your own neural network in Python, no libraries included. And this will give you a better understanding of what's going on under the hood, so to speak. This tutorial will go over the structure of a neural network and its function and how it learns based on data and outputs predictions for the future. Now, the outline will go as follows. We'll talk about that structure and function of a neural network. Then we'll move on to the input and output data and how that's represented in our neural network. Then we'll talk about each neuron in the neural network and how that's activated. After that, we'll talk about how many neurons will work together to perform what's called forward propagation. And this is what a neural network uses to actually predict results. Then we'll briefly touch on the cost and loss functions, what they are, and how we use them to quantify the accuracy of your model. And finally, we'll talk briefly about gradient descent and backpropagation and how our neural network learns based on the data that's given to it. So to start off, let's input all the data that we need and the libraries by pressing Shift-Enter on each of these tabs. We'll also put in functions to initialize and resize our data. You can look at these on your own time. Now let's look at the neural network. What exactly is a neural network? You might hear a lot about it in big tech companies. You're hearing left and right about an AI learning how to fold proteins, or an AI robot learning how to walk on its own, or how Amazon gets to learn what you want to buy and incessantly advertises those items to you throughout the internet. All of that is being done through neural networks. And neural networks, in their essence, take in large amounts of data and they learn. And they take that data and based on that data are able to predict future values given completely new data they've never seen before. So that Amazon algorithm that takes a look at you buying parts for your PC, it'll learn that this person likes computers. And so they'll keep on advertising to you new computer parts or things that you might have clicked on before. Neural networks are a very interesting and exciting field of technology today, and they're changing entire industries today and how we look at the world and how we operate in it. But I want you to leave this tutorial with an understanding of what exactly is going on in these neural networks under the hood. And we'll start all of that off with a simple neural network, as shown over here. You have what's called an input layer, a hidden layer, and an output layer. This input layer represents all the information that you're feeding into your neural network. For example, that click that you made on a product on Amazon, or maybe that Netflix show that you watched and maybe even rated. It'll go through very complex calculations over here in the hidden layer that the neural network learns to do based on previous data. And then finally, it'll output a prediction based on that input that it was given. So if Amazon wants to find out what to advertise to you, it'll input all of the information that they have on you, of your clicks, your interests, what you've browsed online. It'll come to learn what you like, and then it'll output recommendations for new advertisements to send to you. Now, each green node represents what's called a feature, okay? Now, a feature is a single numerical value that holds some significance to the neural network that it can use to learn. Let's say I wanted to buy a room. If I wanted to do that, I'd maybe want to know how big the room is, right? So this green node might represent the square footage of the room. Maybe I want a really new room, one that was built recently. This green node could represent the date that the building was built. And using that information, it can predict perhaps what the room price would be. If it was new and very large, it would be a high price. And it learns that based on previous input labeled data. So we showed it 100,000 rooms, old and new, and we showed them what they costed. Based on that, our neural network is able to learn what the value of each room may be based on that input information. So machine learning really occurs in two steps. First, you train or fit your model, and then you predict. When you train or fit, your neural network is learning based on that labeled data. Remember that we gave it. But how exactly is it learning or fitting that data? What does it mean to fit that data to begin with? Well, notice these arrows over here. These arrows are what's called weights, and each node layer has a bias as well. And we'll look at how we train these weights and biases, and how these weights and biases contribute to the calculation of the output layer later on. And then finally, you'll be looking to use your model, hopefully, to predict new outputs. So our model remembers these weights and biases that it learned based on the labeled data. And given new unlabeled data, it's able to predict maybe what the value of that data would be. Now, that's a lot to take in, and I think the best way to go about this is to go through an example. And the example for today is creating a cat classifier. So suppose you're a cat aficionado and you want to take an image and run it through your neural network and have it tell you whether or not that image is of a cat. We'll be doing that exact neural network today, and you'll be building it from the very foundations. So let's take a look at our input and output data. We're looking at cat images, right? Well, how exactly do you create features from images? Well, let's start off by calling our input image X, right? Let's say that X is a 64 by 64 image. That means it has 4,000 pixels. Now, each pixel has an R and G and B value. RGB stand for red, green, and blue. Each pixel on your computer has those three values, and those three values can represent any color that you wish. So if we were to take the color value of each pixel as our input feature, we'd have 64 pixels by 64 for width and height, times 3 for RGB, will come out with a whopping 12,288. So our number of features is just that. Wait a minute, each green node represents a feature. That means our input layer for a neural network is massive, with 12,288 green nodes going all the way down. And that's what comprises the input layer of our neural network. Now, if we wanted to stack that all up as those nodes, the best way to do it is to represent it as a vector. Remember how our input image is called X? Well, X will look like the following. It'll be a vector of size n by 1. And here it has 255, 52, and so on for n values. 255 could be the red value for the first pixel at the top left corner. 50 could be the green value for the top left pixel. And 2 could be the blue value for the top left pixel, and so on and so forth. Now let's look at the output of our neural network. Using all this information, what is it going to output? We want to classify whether or not the image that we're looking at is of a cat or not a cat. So it's a simple Boolean, yes or no, 1 or 0. So if we wanted to think of our y as a vector, so to speak, it would be basically just 1 by 1. It'll be a single value of either 0 or 1. Now this works great if you're looking at singular images, but oftentimes we want to look at thousands or even hundreds of thousands of images. How do we do that? And moreover, what benefit could that bring? In comes vectorization. Vectorization is the process of stacking our inputs together. So instead of maybe inputting one image into your neural network, suddenly you have M images, however many you want, 1,000 or 100,000 images. Now, what's really cool about vectorization is that it actually makes use of GPU technology and even CPU optimizations. Computers are just really good at multiplying matrices. And so in AI, we use that to our advantage. So remember that our vector that we first created is of size n by 1. And y has a size of 1 by 1. How do we extrapolate that to m training examples, m images that we want to show our neural network, and maybe teach it with those values? We'd simply have to stack them up. So suppose you have these n features over here that represent your single vector up here. But instead now you have each column representing a training example. This is an image, this is an image, this is an image, and so on and so forth. We have m training examples, m columns, and n features. Remember, n we calculated to be 12,288. Similarly with y, we'll count every column as a training example. So we'll say it is a cat, it isn't a cat, so on and so forth. So let's take a look at our raw input data from our data set. You'll notice over here, it's 209 images by 64 width, 64 height, and 3 for the RGB values. Now, this isn't very useful for our neural network, so let's change that around. We'll use our resize data function, run that with Shift Enter. And now our input X looks like this. It's 12,288 because we collapsed these 3 dimensions. And then we really took the transpose, we shifted around the values to make it easier to calculate with the neural network. Similarly with Y, you have 1 over here and for 209 training examples. So now we know what our input looks like. We have each green node representing a feature, and we've stacked on M training examples. So M of these columns of green. Now we need to look at how our hidden layer calculates based on this input. What does each neuron here do? Let's take a look. So each neuron is what's called activated. And the activation is sort of the output of the neuron. Each neuron is a function of the previous layer, and its output will be used to calculate the next layer, or if it's the output layer, that will simply be the output of our neural network. So let's take a closer look. We have our input features and we know what our output looks like. So let's take a closer look at what each neuron does. Now remember how we mentioned that there are what's called weights and biases to each of the arrows and hidden layers respectively. We use those to calculate for our neural networks. Let's use this as an example. Once again, we have our green nodes, input layer. We have our hidden layer. Let's zoom in and look at just one neuron, okay? And notice that this neuron is taking an input from each feature. And it outputs just one arrow, and that's used in the next layer, which happens to be the output layer. Let's take a closer look at what each of these arrows represents and what a bias is. So each of these arrows, we put together into a vector called W, or rather a matrix. In this matrix, we multiply it by X, which is our input features, and we add some bias B. The bias acts to simply give us more options for linear functions that we can represent. If you didn't have a B, all your functions would be going through the origin. But now we have a lot more that we can work with. So our first step is to calculate this linear function of X and the weights W, and of course, bias B. Let's call that Z. Let's take a closer look at Z and how the linear function is calculated. Now these weights, this matrix over here represents all the weights for the entire layer, the hidden layer. So notice that we have 4 nodes in our hidden layer, and we also have 4 rows here. Each row represents the node in the hidden layer. And what about these columns? What do they represent? Well, notice that we have 1, 2, 3 weights. We have 1, 2, 3 input vectors. Each of these weights is actually one of these arrows. You have arrows going from the input features, going into each of your neurons. You have 3 times 4, and that's the size of your weights matrix, 3, 4. And of course, you also have X values over here. That's your input features. And the bias B. Remember, our bias is just a constant value that we add on so we can represent more functions. You'll notice that there's one for each hidden node in our layer, B1, B2, B3, B4. So we have this linear function. Why can't we just stop there? Well, suppose you calculated your neural network based on this linear function. All you're doing is really just multiplying values by X, and maybe adding them. The best you can come up with is some kind of output plane. But neural networks can do a lot more than just that. They can find faces. They can model complex functions. And planes just don't cut it. And so we need some introduction of what's called nonlinearity. This nonlinearity is what introduces curves to our function, introduces complexity to our neural network. It's what's capable of making our neural network powerful. And that's the second step that we perform over here. We perform a nonlinear activation function called G on Z. Remember, it adds nonlinearity to our neural network. Now, we will be using 2 activation functions, one called the sigmoid function, then the second called ReLU, or rectified linear unit. And that can be represented over here. A is equal to G of Z. A is G of each element of Z. So we're performing this nonlinear function on our linear function. And our output, our activation, that A is what gets fed into the next layer. Now let's take a closer look at a more concrete example using this figure below. So let's say we have the input layer. It has only 3 features. Remember, we have M training examples. So our X will be of size 3 by M. Now, let's look at the hidden layer. We have 4 nodes, right? But we want each of those nodes to have a value for the M training examples, right? So this hidden layer we'll call A1. That is 4 by M. That's its size. So we know that the weights multiply by X to give us A1. So what exactly is the shape of W? We could pause to think about it, but the answer is right here, 4 by 3. So let's take a closer look. Z is W dot, so the dot product, X plus B. Now, B is applied element-wise anyway, so it won't affect our matrix size. So let's focus in on W and X. W is of size 4 by 3, and X is of size 3 by M. If you remember from linear algebra, you cancel the middle values, 3, 3, and our output will be 4M, exactly the size of A1. So let's try to generalize this a bit. The size of weights W is current layer size, comma, previous layer size. So in this example, W is current layer size 4, comma 3, our previous layer size. That's exactly what it is over here, 4 by 3. Let's take a look at B. Since we're adding B to the product of this, B will be of size current layer, comma 1, because you have a bias for each node here. The really attentive one of you might notice, what about the M? What about the vectorization? Well, we use what's called Python broadcasting, and you'll see an example of this later on, but we'll just add B1, B2, B3 to each of the M examples. Let's take a look at just that. Let's take a look at the vectorized implementation for M. So we have our weights, once again, completely unaffected by the fact that we have M input training examples. So we multiply this as follows. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. Notice that's happening for each of the training examples. The same calculation, W1, 2, 3 by X, 1, 2, 3 is happening for each of the training examples. So the extra columns doesn't change our calculation. It just performs it multiple times over. Now we'll have a matrix like this, where each row represents a node in the hidden layer. Each column represents a training example. And we have B1, B2, B3, and B4 added to each value element-wise in each of the columns. And this is what's called broadcasting, and it is a feature of Python to be able to do this. And it, in the end, makes the calculations just the same. Notice that Z, W1, X1 plus B1 is the same as up here. It's just now we have many X's, X1 to XM, and over here we just had just one X. Now let's take a look at the activation. A, we applied it element-wise over here, and we do the exact same thing in the vectorized implementation. It's G of each element in the Z matrix. So let's try to apply this. Let's fill in this function. This function initializes our parameters, particularly B and W over here for each layer. And the size of each layer is contained in this list layer dims. So what do you think W and B should be using what you've learned above? Feel free to pause the video and try to find the dimensions right now. I hope that you took the time to try out this exercise, and I'll be showing you the result right now. Over here, remember that W is the current layer, comma, the previous layer. And we're at layer L, right? So we do just that. Layer dims at L, comma, the previous layer. Layer dims at L minus 1. Similarly, B will be the size of our hidden layer. So layer dims at L. And the second dimension will just be 1, because remember, we are broadcasting to each column in our matrix. And just like that, you've initialized your parameters to get started in your neural network. Now let's take a look at our activation function, G. Now G can be several activation functions. There are many, but we'll be using 2 of those functions today. Those 2 are the sigmoid function over here and the ReLU, the rectified linear unit, shown over here. So to reiterate all that we've learned, we calculate Z is equal to W times X plus B. Then we calculate the activation based on G, which can either be the sigmoid or the ReLU. And finally, for purposes you'll find later on, we'll be caching our values in the next steps. So let's fill in the sigmoid function over here. Feel free to pause right now. I hope you had a crack at it. Now, the sigmoid function looks as follows. 1 over 1 plus np.exp. So e to the power of negative z. And this will be applied element-wise to z. Next, let's fit in the ReLU function. Looks as follows. np.maximum, 0 and z. If 0 is negative, it'll just go to a value of 0. If 0 is positive, we'll just return the value of 0. Next, let's look at the linear forward function. The linear forward represents the linear portion of our calculation for the neurons. Z is equal to W dot X plus B. Take a moment to figure this out using NumPy's library and the NumPy function np dot dot of 2 matrices. The result will be as follows. Z will be W, np dot dot, W and A over here, A representing whatever our previous layer was. And our examples over here, our previous layer was just the input layer, X. But if you had several layers in your neural network, it could be just about anything. And then we add plus B over here. Now moving forward, now that we've calculated the linear portion, let's look at the activation portion of our function. We calculated Z using our linear forward. And if our activation is sigmoid, we're performing the sigmoid function on what? The answer is Z, right? Similarly, we calculate Z over here. And based on our activation that we require, we'll perform ReLU function on, that's right, Z. And make sure to run each of these cells so that they actually compile. Now that we've learned how to calculate the value for a hidden layer, how do we get to our output layer? How do we move from here to here? Well, if we could do computation for 2 layers, we can do the exact same for any other 2 layers right up until the end. And that's what's called forward propagation. So forward propagation takes you from the input layer to the first hidden layer, to the second hidden layer, and so on and so forth. You'll notice over here, 4L in range of 1 to L, L being the number of layers in our hidden or in our neural network, will perform the linear activation over and over, saving our previous A and inputting it into the linear activation. Now, this is a small architectural detail, but for most of our layers, we're using the ReLU function. And in the final layer, we're using the sigmoid function over here. Now let's move on to the cost function. How do we quantify how well our neural network did? Well, it's done using this formula down here, where y hat is the output of our neural network and yi is the actual value of the input that we gave our neural network. Now, this equation over here may seem somewhat confusing, but let's break it down. We're summing over all of our M training examples, and we're saying that if y is 1, we want the y over here, our predicted y, to be 1 as well. And if it is 1, then this will all equal to 0. That makes sense because if we predicted the same as the actual value, we want a 0 cost. We did well. We don't want to be punished for that. Similarly, if y is equal to 0, right, then this will equal to 1. And if our y is equal to 0, this will also cancel out into 0, giving us no cost at all. Now, on the flip side, let's say this was 1, and this was, or rather, our prediction was 0.1. We thought it didn't make it. The log of 0.1 will be a larger cost. And it'll be a negative value. This negative will be canceled out over here. So it'll give us an actual cost, telling us that our neural network didn't do well. So take some time to implement this function over here using the NumPy functions, np.dot, if you've learned before. You can also use the np sum if you would like as well. The dot can be used in order to use matrix multiplication to simply forego the summation, but you can use a summation if you'd like. And here's the answer to the cost function. We divide by m times negative np dot, so we want the dot product of y and np dot log al. And we transpose that so that they essentially cancel each other out. They multiply and add. Now you can convince yourself of that, but I will not go into that in this video. AL represents our final layer, activation for layer L of our neural network. The second one is NP dot 1 minus y, just like our formula. And we'll perform np.log 1 minus al, again, transpose dot t in order to sum the entire thing. We'll run that, and we've compiled it. Now let's move on to backwards propagation and gradient descent, really where your neural network is doing all of its learning. Now, we've talked a lot about how we make predictions, how we propagate through your neural network, but we haven't really talked about how we fit it. How do we fit our neural network to our data? Well, it's quite a complex process, and it takes some derivation and calculus, and that's out of the scope of this tutorial. But I want you to have an intuition as to what backward propagation is doing and what gradient descent is, and how neural networks use these in order to optimize our neural network. So let's take a look at our curve over here. Now let's say that this represents all the possible costs of our neural network. Up here, your neural network is horribly optimized and is not fit to your training data whatsoever. And down here, your neural network is optimal. It has been trained and fit to the data, and it can make accurate predictions on your data. This would represent the cost function. If you have a low cost, that means your neural network is accurate. If you have a high cost, it's not so accurate at all. So let's say you initialize your values to a random value. Let's say we're at the orange point over here. How do we get our neural network to get down to the lowest cost? Well, it works as follows. Notice that we have a slope over here, right? The slope is positive, but we want to go down here, right? Now, if we just took our value for our orange point and subtracted it by the derivative, the slope here, if the slope is positive, then we add, or we go in a negative direction, we'll get closer and closer to our cost function. Similarly, let's say that the orange point was over here, our slope would be negative. And so we go the opposite direction. We go positive down the curve, positive down the curve, because it's a negative slope, positive down the curve, right until we are at the optimal point for our neural network. And once again, I won't go over how exactly that works. There are many courses online in order to teach you how to do just that. But I want you to come out with the understanding of the intuition behind that gradient descent, that use of our slope going the other way, the opposite direction of our slope, in order to reach our optimal zone, our lowest cost. Below are the functions for the backward propagation, and we won't go into those today. However, with many modern deep learning frameworks, manually coding your backpropagation is actually no longer needed. A lot of the time, you only need to compute the forward propagation only. And so we'll leave this for another day. But make sure to run each of these cells in order for our model to be able to get trained. So we will iterate over this model for some number of iterations, or perform a forward propagation. And this forward propagation at the beginning may be very inaccurate because we're still just trying to train our model. Then we'll compute a cost, get an estimate as to how well our program or our neural network is doing. After that, we'll perform a backward propagation to find our gradients, and then we will update our gradients over here through the update parameters. You'll notice in the update parameters, we're subtracting the gradient. We're subtracting the slope. If it's positive, we want to go negative. If it's negative, we want to go positive. And we continue to iterate just like that. Make sure to run that cell, run our prediction function, and let's finally give it some data. We have our XY which is our data set. We have our X test and Y test. This is data that our neural network will not train on. We'll resize our data and give it an architecture for the layers. We'll start off with our input layer, then the first hidden layer, the second hidden layer, the third hidden layer, and finally our output layer. Let's train it for, let's say, 3,000 iterations and tell it to print the cost. And notice how after each iteration, or each 100 iterations, the cost is slowly going down. It's inching closer and closer to zero. That means our neural network is learning. It's using the gradients to change the weights and biases in order to reach a more optimal solution that can predict new data as it comes. So you see, now that we've finished training our neural network, the cost has decreased significantly from a whopping 77% all the way down to 0.07. So our neural network has really worked hard to adjust the weights and biases to be able to predict whether or not the image that we feed it is a cat picture or not. And let's say we tell it to predict our X and Y. We come out with an accuracy of a whopping 0.99. So 99% of the images that we feed it, it is able to correctly predict their values. But let's say we feed it all new data that's never seen before. How does it perform? Let's run this, and it comes out with a whopping 82%. So let's take a look at the images in our test set, the set of images that our neural network has never seen before. Taking a look at this, our model predicted 0.56, so it was decently confident that this was indeed a cat. And that ends up being the case. Let's change up the index. Let's say it was at index 12. This is indeed a cat, and our model predicted with high confidence, 0.99, that it is a cat, and indeed it is a cat. Let's say we went up to 20. Again, this is also a cat. So you can see now that neural networks aren't as elusive as they may seem. They don't need to be a black box. In essence, they're matrices of weights and biases. There are connections between the input layer, the hidden layers, and the output layer. And they're trained based on labeled data that it learns and adjusts its weights and biases based on the results of that input's labeled data. And so I hope with this tutorial, you've come to have an appreciation for neural networks and the way they function. And I hope that you come out understanding the structure, that ubiquitous structure of neural networks that we see everywhere. And I want you to hopefully take this tutorial as a good first step to move on to bigger and greater things and spark your love and passion for AI and neural networks. I hope you guys had fun, and I hope you guys followed along with the tutorial. Please leave any questions in the comments below, and make sure to attend even more AI Society tutorials. Thank you.